Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 4 of a little mini-series that I'm doing on one-way fixed effects ANOVA. And here we're finishing up a derivation from part 3 actually. And I'm going to flash this just as a reminder. We partitioned the total sum of squares in part 3 and we were looking at the expected value, the mean sum of squares total. And in our derivation we went from a matrix form to a scalar form, and I said next video. And then we also did the same for the expected value of the sum of squares treatment. We went from a matrix to a scalar and we said next video, mainly because this video was getting long and I wanted to keep it as short as possible. So here we're going to do those two derivations. So we're going to complete the missing steps from part 3. So the first one, we took this matrix form and went to a scalar form. Now, what we're going to do this in steps. We're going to take this x and multiply it in. That's what we get here. And now let's look at just j of x. So let's examine j of x. Now, one thing to remember though, and this I find so fascinating, J is a perpendicular projection matrix on the column space of 1s. So any dangling vector that we multiply, we pre-multiply by J by, it's going to shove it down onto the column space of that one vector. So it's going to be a constant vector of some value. And so here we have a matrix, and so it's going to take each column and shove it down onto the column space of the one vector. So we already know that beforehand. And so when we see the final result, it shouldn't be surprising. So J is this. So U stands for, it's a matrix of all ones, and it's NA by NA. Now, X is in this form. Remember, the first column is all ones corresponding to mu, and then these correspond to the tau parameters that are picked off when we do that multiplication. So this is all ones multiplied by all ones here, so it's the sum, it's NA. But then you divide by NA, and if this is a matrix, so that top left is going to be a 1. Now, if we use the second row, multiply this, we're adding up NA ones, which is NA, divided by NA, and it's going to be 1. So every row that we go down, we're going to produce a 1, so we get a 1 vector. Now, that is clearly in the column space of the 1 vector. Now this one here, so we take the first row and multiply it by this column, and we add up N1, so we get N divided by NA, so we get a 1 divided by NA. So this first entry in column 2 is going to be a 1 divided by A. And as we go down the row, see every row is the same, right? So then when we multiply every row by this column, we're going to get N, and then we're going to divide it by NA. So it's going to be a 1 divided by 1A. And now notice, look at this second column. So we took J times the second column and it shoved it down onto the column space of the 1 vector, which means it's a 1 vector with some constant. Well, every other column is going to be similar, right? Because this row times this, we're going to get N divided by NA, so it's going to be a 1 vector and divided by A. So this is the result. But now, if we just look at these columns here, we can kind of left factor out an A, and then what's left is a matrix of all ones. So we get this. So this is the result of JX. Now, let's do the next step. So let's multiply this B in, and then let's look at JX times B, which is this. So here's JX, and here's the beta vector, mu tau 1 through tau A. So when but already we know J, we take this vector and pre-multiply it by J, so it's going to shove it down onto the column space of 1 So we already know what it's going to look like. So we take this vector and then, multiply the first row. And actually it's all ones, except for this piece is 1 over a. So that 1 picks off a mu, and then these are going to add up these and then divide by a. So it's going to be the mean of the taus. And actually every row is the same. So we could left factor out that constant, and it's the 1 vector. And so that's jx beta. Now the next step, so take that beta in, let's look at x beta. And now this is a little bit tedious work, but it's so worth it in the long run, especially when we start doing two-way fixed effects in ANOVA and beyond. So when we do this multiplication, it's going to pick off mu and tau 1 for the first n. It's going to be the same. So it's going to be a 1 vector times this constant. And then when we get to the n plus 1th row, it's going to start picking off tau 2 instead of tau 1. And as we go down, then this last row is going to pick off tau a. So we get this. So every n components is just this constant. And the last n components would be this constant. Now let's multiply ij times x, which is essentially, you take this minus this, and we're going to get this. So every n, remember this is just a constant vector of this. So every n components, you take this minus that, which is what this is. And then the next n components, and although if we do the last one, and then look at the last n components here, this minus this, the mu's cancel, and we get tau a minus tau, the mean of the taus. So ij, remember we're here, we started here. This is a perpendicular projection matrix, so we can multiply it together, and then it's symmetric, so we can transpose it, and then we can untranspose that, and we're back to here. But we get this. So this is a vector dotted with itself, so it's going to be squared of something. So remember, look at this, we're adding this squared n times, and then the next one, and so we get this quantity. And that's what we wanted to show. Now notice the second quantity is this. So what's different is it's I minus j, and this is m minus j. But when you multiply that x into here, we get jx, and then since m is a perpendicular projection matrix on the column space of x, it projects it back down into x, but we already live in x, so it's just x. So it's this. But notice, this is exactly what we calculated up here. So we get the same thing. And that's the proof from number 2. Now a few notes. When we look at this quadratic form, instantly we know that it's positive semi-definite. And you might ask why. And the answer is because this is an idempotent matrix. It's actually what's called a perpendicular projection matrix, which is symmetric and idempotent. So it's a perpendicular projection matrix onto its own column space. But the important part is it's idempotent, which then means this quadratic form is positive semi-definite. It's 0 or positive, or non-negative. And you can see it better here, that this is clearly non-negative because we're adding up non-negative things, right, when you square something. So this is 0 if and only if every term is 0. And every term is 0 is only if this is 0 for every I. So in this case, the true model becomes, remember this is our original model, but this is just a constant, right, if they all equal. So we can just lump it into this constant. So we're modeling a constant times some error. And so thus, there's not a treatment effect. Now this concept will come into play in, I think, part 5 when we look at f-tests or confidence intervals. Now in part 2, when we were looking at estimating the parameters, we introduced what's called a side constraint. And now I think it's mixed emotions whether this side constraint is a good thing or not. But some statisticians do it or use it, and so we're going to cover it. So if we look at this quadratic form again, and we showed it was this, but if we have this side constraint that the sum of the tau's equals 0, and this average right here is the sum of the tau's divided by A. So that's 0, right? Because the sum of the tau's is 0. So then this reduces just to the expression of the sum of the tau I squared. Now this term is 0 if and only if every term is 0, which means every tau I is 0, and this is for all I. So in this case, our true model becomes, yi equal mu plus epsilon. So which is essentially the same. It's yi equals some constant plus air. And if this is our model, there's no treatment effect. So in either way, we're going to use this quadratic form here, or this sum, in our f-test and confidence intervals. Now, interpretation, just to sum it up, this is 0 if and only if there's no treatment effect. Now, in our f-test, this next little proof is going to be valuable. So if y is normally distributed, so we have to assume some distribution if we're going to do tests and confidence intervals. The sum of squares treatment is this, and it's independent of the sum of squares error. Now these are quadratic forms, and I have a playlist called quadratic forms, and in there's the independence of quadratic forms. But basically you multiply these two inner matrices together, and if it's 0, these two quadratic forms are independent. So if we take those two and pre-multiply, so we get m minus j, m squared, m minus j. Well, this is a perpendicular projection matrix, so m minus m goes away, and this is a perpendicular projection matrix on a column space of x, and j consists of columns of the one vector, which is in the column space of x, so this projects it back down onto itself, which is j. So we get j minus j, which is 0. So these two sum of squares are independent, and that's going to be vital in part 5 when we do f-tests and confidence intervals. Okay, well that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.